Hello. So, good morning, good afternoon, good evening, whenever you're listening to this. My name is Leo, and I'm super excited to be here at the first SDPRA workshop. And today I'm going to talk a little bit about how my group at Snap Research makes research, how the constraints of doing research in an industry lab actually affect the outcome of our research, and try to make a case for simplicity, how important it is to not only focus on this very huge methods and so on, but also value like those very simple changes that we can make, but they can make a big impact, right? So just starting here, again, my name is Leo. I'm a lead research scientist at Snap Research, which is the research branch of Snap Inc., the company behind Snapchat, Bitmoji. This is my Bitmoji, by the way, if you're not familiar with those spectacles and so on. And Snap Research, well, Snap as a whole, the company, is a very innovation-focused company. And Snap Research, we have this motto of science empowering creativity. The idea here is that we try to create knowledge. We try to empower the innovation, fuel the innovation of the company, right? And we're split into four groups, all of them in the United States. First, the computational imaging group that's in New York City, led by Shri, also professor at Columbia. We have the human computer interaction group in Seattle. We have the creative vision and the computational social science group, both in Los Angeles. And I manage and lead the computational social science group. Talking about my group a little more specifically, so the whole of the role of the group is basically try to understand behavior in society as a whole, but through the lenses of Snapchat, right? So we kind of try to merge natural language processing, computer vision, data mining, behavioral science, a lot of disciplines, and try to put them to work together in projects that mix everything and provide insights into like human behavior and insights that can actually improve the experience of all the users in our platform. And I want to highlight that part because that's kind of providing insights into human behavior is very broad, but then we actually add a constraint at the end. And this is a very important constraint because it kind of shapes the way we do research. I'm not saying that everything we do needs to be directly applicable to what we're having here, but we have this model of the science of a purpose, not just doing science for the sake of science, but we're doing science to improve the way the company operates. And we're kind of doing research in a company that cannot afford yet, we're going the right direction there, but cannot afford yet just do science for the sake of science. We're doing science with a purpose. And to do science with a purpose, we're looking at the 5-10-year horizon. And even though like some of the work we are doing now is not directly applicable to do existing products, existing format of the company, the goal is if we solve this problem in the next 5-10 years, that could be beneficial for the company. So that's how we think about projects when we're picking them. We love publishing. You're going to see a lot of the work we've been doing, but most of those publications, they do operate under constraints, at least one of those, but we always have those in mind, even when we don't apply them. For example, we need to make things scalable, reliable. We need to be able to update models, which is something we're not usually doing in academia. We need to be compliant with all the very strict privacy regulations that Snap imposes on its data, interpretable, fairness, return on investment, and so on, so on, so on. There's a lot of different constraints. Depending on the project, we might be constrained by one of them, by several of them. And sometimes actually those constraints create the projects for us because otherwise, without any constraints, those would be very easy to actually solve. But under our constraints, they're very critical. So there's a lot of constraints. I actually separated 4 of them: scalability, reliability, model updates, and privacy. I'm going to talk about projects that actually operated or were inspired by all of those constraints to show that those constraints are indeed important for the research part, not only for the company. And because we're operating under those constraints, you probably won't be seeing a lot of this. You're not going to be seeing a lot of this very famous approaches now, like the transformers methods that use trillions of parameters, huge data set sizes. We do have huge data set sizes. That's true. Like we have more than 250 million people using our platform every single day. Of course, because of the privacy constraints, most of that data is not available, but the one that's available is still a huge amount of data. But I'm not going to be talking about those huge models. I might be talking about some complex models, but I'm going to emphasize the other methods that came after them or that came parallel to them that actually can bring some results. And I want to break it down to the 4 constraints. Let me start with scalability. Okay. And for the scalability issue, we actually, I want to talk about one specific topic that actually became, well, at least 2 publications, but a couple of several projects that we have at Snap, which is a multi-level document similarity test. Okay, so let me give an example of this test. This is a test that we've seen a couple of times. I'm going to show 2 specific tasks that rely on that were important to us. One of them is this bug report to the application system, right? So why do we need that? Like our platform has, as I mentioned, millions and millions of users using it every day. We have more than 3,000 people in the company working on improving the system. We have features being released every other week. So bugs are going to happen. We need to prepare for those, And that means that on Snap, there's this specific feature called shake to report. So basically, you can grab your phone, you're using Snap, you shake, and then a pop-up shows which says, look, write down what you problems are facing. If you want, we can add the screenshot, and that's going to give you allow us to know what's going on with your bug. It's going to send us this fact trace, send all the information we need, and we might be able to fix that bug. So people use that a lot, and because we have so many users, you can expect. And when we started this project back in 2018, we expected this number to keep increasing. It is true that it did increase as much, but when we were working under that scalability issue, we tried to make the model to be scalable and try to minimize how many models we actually had to train and so on. So example here, right? So bug reports. People could be writing those bug reports and they shake like this. The screen is blank when I use the camera, my camera is black, my camera is blurry, and so on. They could write anything. And the way the 2 things we need to do with those bug reports, specifically on the application side, is there are 2 ways. One, they could be the same bug. And why is that important? Because if we can aggregate all the bugs are about the same, all the tickets that are about the same bug, now we can prioritize. We can know that if there is 1,000 people complaining about this bug and 1 million people complaining about this other one, hopefully never going to have 1 million people complaining about the same thing. But if you have 1 million people on this, 1,000 on this, probably need to fix 1 million people bug first, right? And if we're talking about the exact same bug, we can try to find potentially 2 tickets that mean the same thing. In this case, we could have like, my camera is all black and the screen is blank when I use the camera. They could potentially be the same bug, right? It could be just a person opening it, everything is black because that's the default color. And then they would write it either way. But the other way that we could think about it is that after we are able to prioritize, how can we actually know who should fix it? As I mentioned, thousands of people in the company, well, not thousands, but like hundreds of features that we're working on. So the topic of the problem, right? Like the feature of the problem is another thing that we would like to do. So let's say here that my camera is all black, my camera is blurry. They're both different bugs, but they're both about the camera. And we want to probably be able to also aggregate them by this level of topic, right, on the feature level. So that's one of the projects we worked on. I'm not going to go into a lot of details of the solution. If you're interested, the name of the paper is at the bottom here. But the gist of it is basically that we train one single model that would only use the labels for one task, the duplicate task. So it would just show 2 duplicates to the labelers. They would just label if they're duplicates or not. And by using that and some different kind of attention mechanisms there, we'll be able to also learn unsupervisedly, in a sense, that to duplicate them between the topics, right? So you can see on the right here, the right-hand side, you can see the graph of two attentions, and the self-attention is looking at the topic, and you can see it highlights style, which is the feature, and the conditional attention is actually looking at the bug, so it's highlighting totally black, which is what makes those bugs to be the same. And so we trained that, we published the paper, and we were happy with that because now we only have one model that we have to run on each pairs. Those pairs, because you're comparing pairwise, that's like quadratic with the number of pairs that you have. So it's actually much more expensive, even if you don't have as many tickets. And as we were implementing this and looking at it, there's the good part here is also like this interpretability of seeing why they're similar to each other. But then a couple of months later, we have this new task. This task came from the release of a new feature called Happening Now. You can check that on the app. Excuse me. And the Happening Now feature works like this. You have a stream of several news sources from different countries and so on. And the Happening Now kind of curates a list of the top news that you should be reading this day. And to do that, it kind of has one. If there's a lot of news articles talking about it, kind of similar to the Shakespeare report, you want to be able to cluster them together to have a prioritization system. You also want to be able to not show the same news twice to the same person. And if the person wants to explore some category, that person should also be able to do it, if you think about any news website. So the second problem that we had was this. We want to be able to categorize the news articles into two levels now. We're going to call them abstract, like we were calling the topic before. We're going to call it granular, and we're calling the same bug before. In this case, the topic here is actually the topic: politics, sports, I don't know, entertainment, and kind of those categories that you can categorize in news articles. And the granular part is going to be, if you have two news articles, are they talking about the exactly same event? So similar to the camera being black and being blurry and being blank, and two of them actually meaning the same thing, the other two being the same topic, we could have, for example, a news article that says that Donald Trump visited India, right? Donald Trump is the previous president of the United States. And then we could have another one that says Joe Biden visited India. Here, the only thing that changes is the entity, even though they are both presidents of the United States at the time that the news was written. So how do you actually tell them apart? Because they are definitely about the same topic. They're still talking about politics, about the president of the United States visiting India, but they are not the same event. So on the granular level, that becomes a much trickier task. And we start thinking about that constraint, the constraint of scalability that we talked about before. And that's very similar than before, but now especially important that you get the duplicate side right. So what we did is that this time we actually labeled both, not only the duplication similarity, but also the topic similarity, right? And you can see the results on the paper on the bottom here. But basically, the first thing we thought about is let's get an end-to-end system that uses like a Roberta model, a BERT model, like end-to-end, and that's gonna be giving us great results. And that's true. Like the first thing we did was applying that for abstract level, topic level. End-to-end Roberta transformer method was great. You just fit both of them together there, and then you'd fit that end-to-end, and you would train a model on top of what you get after the Roberta method, and that's it. You would get the best results for topic detection. But for the granular method, when we tried the same thing, it just didn't work. Actually, did very poorly. So we started exploring different simpler methods. And the truth is, not only the end-to-end method was not the best option in this case, but encapsulating, like using the vector representation as a TF-IDF vector would give us a much better result. So we realized that TF-IDF actually was the best option here. Basically, what we would do in this situation, which is not end-to-end, is we would get the two vectors, train the vocabulary on the corpus that we had. Then we'd compute the cosine similarity between those vectors and use that similarity as the input to a model. And then the model would only use the similarity there. We might have like similarity for the header, for the body, and so on. The model might have to learn to weight those. And then using that similarity would get predict if they're talking about the exactly same event, and that showed much better results. The paper, we also showed that we can actually merge both approaches there, like the transformer model and TF-IDF. But the gist of this part here is how can we focus on the simple things, right? So let's talk about the TF-IDF. One great thing about the solution that we got at is that it's super fast and easy to retrain, right? You can just basically every week get all the corpus of text that you got in the previous week and kind of retrain the TF-IDF method. And the truth is, you don't really need to retrain the model. You only need to retrain the vector, because now you're using the similarity. And what we learn is it takes a long time for the actual similarity to the model that uses the similarity to get outdated. It's very different than the vocabulary that changes every week. So that was a fascinating way, because now we have hundreds of thousands of news articles coming in every month. We have all the pairwise comparisons. Of course, we do some smart not to do like all the comparisons necessary, but still it's a lot of comparisons. And now what we need to do is retrain a TF-IDF vector. Very easy to do, very easy to understand what the vectors mean, right? We can basically just look where the overlap on TF-IDF, like the cosine similarity comes, plot a graph like the one on the right here. And it's several order of magnitudes better than BERT. We know what's going on there because we can just look at the vocabulary, and can be combined with more complex models if needed. So that's something we never think about analyzing TF-IDF in this case and comparing that to transformer methods if we didn't have the constraint, right? Probably we would just keep throwing more layers there and try to figure out a better way to do it if we didn't have the scalability constraint. Another constraint, as I mentioned, that TF-IDF gives us here is that it's very easy to retrain. And that's what I'm gonna jump next, right? Here, I mentioned this multi-level document similarity thing because that's a problem that if we keep putting more layers on transformers, that's not gonna help. What actually helped was going another way and thinking about how to leverage simpler methods. Same thing for model updates. Model updates is something that, at least in grad school, I never thought about it. Maybe nowadays it's a bit more common, but it's been a while since I left grad school. But the idea of this is here. When you train a method and you publish in your paper, you might be able to, for any task that you have, train a method that on any given task get like a 93% F1 score. Let's say that you were able to do that. That's a big achievement. If you're writing a paper, you write a paper compared to the other ones that get a little bit less than you. And you would publish the paper, and a lot of times that's it. You're gonna put it open source, and you might not even have to support it anymore, and so on. Which is not true for models that you put in production. So let's say we have a system that, I don't know, ranks friend recommendations. I'm making this up, and you train the method. It's 93% good, and then over time, that's what might happen with it, right? With time, it might be start to drop performance until you get to a stage where it's below a threshold that we set. That's the minimum performance that we expect the model to do. And when we get there, what you can do is actually retraining the method. So why would that happen? Like, why would the models start degrading performance? And this is a feature called distribution drift, in a sense. There's a couple names for it, but this temporal drift idea is that the distribution of your input is going to change over time, especially in a dynamic system like a social platform. And as it changes over time, your model learned to behave with the original distribution. Now the distribution is different, the model might suffer. And this is very common. Most of the models that you train, you need to keep retraining them. And one way to do it is basically create a method that can actually learn with time and so on. Usually that's harder, right? So one thing that we focus a lot on, and that's a collaboration we had with University of Southern California last year, is how can we create methods that make labeling more efficient? Because that's where, like, labeling is not expensive, but it's not cheap as well. And if you're going to be labeling recurrently, then it becomes expensive. So if we're already going to be labeling recurrently, can we minimize the amount of data that we need labeled there? And can we make labeling more efficient? That's kind of the focus of a couple of pieces of work that we did together with Chiang Ren from USC and his students. And basically, we tried different alternatives there. One, actually asking labelers to explain in plain English how they why they labeled the instance that way. So that would take a little bit longer than actually just labeling, but we found out that it was worth it because our method could learn from it and actually leverage more unlabeled data. Then we worked on Neuro, which was not exactly using natural language, but using like some simple rules that we could teach them easily, and it would get great performance improvements on relation extraction tasks. I have the asterisk there because I just wanted to mention that this got a best paper honorable mention on the WebConf of last year, which was amazing. And the last piece of work that we worked on that direction was Ling Life. That was a demo paper at ACL, where it would incorporate some of those ideas of active learning and so on to try to improve the labeling, right? So those are super relevant, super important. I'm super happy that we worked on those, and we have been trying to apply those in our scenarios here, which is great. But those are a little bit more complex. They do require a neural network that learns to map the explanations or the rules, and they start becoming a bit more complex. And we're going to keep working on those. I think those are super important. But I want actually to highlight one specific piece of work that we recently got accepted at the Social NLP workshop, which doesn't do anything super fancy, but actually get very good results. So let me give an example here. So the focus of the task, the tasking focus actually was the NER, name entity recognition task. And we realized that this is specifically a hard task to relabel because the entities change over time on social media, like every week mostly. So what did we do? We got a bunch of older data, and from several years. We actually used tweets for that one. And we got tweets from several years, and we kind of ranked them according to this score that I'm gonna explain right now. But let's say that we have a unigram, like a word, corona, right? In 2019, the word corona was mainly, like, if you sample a tweet, 99.9999% of times, it would be talking about the beer corona. Could be something like drinking a corona with my butt. That could be the tweet that you're sampling there. The problem with that is then 2021, we started having this terrible virus going over the world, and the tweets might have changed a little bit. They might be talking about mainly the virus, and I'm so worried about coronavirus and so on. And hopefully in 2022, we're gonna go back to the original distribution. We're gonna have beer being the gist of all the tweets related to corona. So this kind of shifting meaning that could be permanent, could be temporary, so on, that kind of throws off most of the models, because if the models were trained, let's say we had a entity recognizer that would either try to detect the beer or virus before, it would probably not get the virus correctly with the data only for 2019. So we regularly retrain those methods. And one thing that we realize is this is kind of a change in volume of dimension most of the time, right? On this case, if the formula we proposed was a very simple one where we would look at the volume of a term, a unigram or n kind of n-gram, but we focus on unigrams, bigrams. You will get the volume at the present time that you want to label. And then you would subtract the volume of the same n-gram from the previous time frame, whatever time frame you have before. It could be the last year, it could be the last couple of years. And then usually they should be the same size, right? And then you divide that by the count of the previous time plus a constant. That's just for smoothing, right? So you don't have a lot of very infrequent terms appearing. And also avoiding any kind of division by zero there. That's why I have that. But then by doing that, now we can score n-gram, right? Like by doing that, that's a very simple score. Any n-gram that we have on our vocabulary could be scored. And now that we have a score for each n-gram, we would just sample, like we could get an average or max or whatever thing you want to add to the as your score function for the tweets. But now you can score tweets based on that, and you sample just the tweets that have the highest values. And by doing that, you can see that first, it's super easy to compute, like super simple to compute. But also, if you want to check the paper on the bottom here, but also if you want to check the graphs here, you can see that especially on low resources, but on all resources setting that we tried, you have a big jump between just randomly sampling data or sampling data using this this approach. Like the gains in performance are very clear for us. And the other cool thing about this very simple technique is that it is reproducible in several data sets, and that allows us to replicate that in other data sets, not only the specific one that we're doing. So that's a very generic one, very simple, very easy to understand if you want to explain to someone, which is also something that's important for when you're doing industry research. And all of that to keep our models updated. And as I mentioned, like temporal drift is important because our models with time, they start becoming less reliable, right? It's not only the performance, but you cannot trust that it's gonna work as expected with time. That's another constraint that we have. So right now, we've talked about scalability. We talked about how can we update models. I wanna talk about reliability as well. How can we train models that are not just overfitting to the training data, and when they go to real life scenarios, they're gonna fail, right? Because the truth is, for a lot of tasks, the data sets that we have to evaluate, to train, they're very small, and creating a reliable model is important. Okay, so talking about reliability, I want to talk about multimodal naming entity recognition, because that's a problem that I believe, and at least as far as I know, it's a problem that started, the multimodal part at least, that we published the first couple of papers on that. And then I've seen a lot of people working on it before, some data sets show up. But multimodal entity recognition is basically this. You're gonna have a phrase, a tweet, could be. You're gonna have an image associated to it. And for each one of the tokens on the text that you have, you're gonna try to predict if they are a person, location, whatever kind of entity that you have, or if they're not entity at all. So it's kind of a token by token classification task. For the two pieces of work that we did, that's back in 2017, published in 2018, one at NACO, actually two at the ACL, one was more disambiguation than recognition. But the two of them, we're trying to merge, like at Snap, specifically, that's where the idea came from. We have very short text, let's say like 4 or 5 words maximum, a lot of slangs, a lot of acronyms, typos, and so on. So just using the text there, you miss a lot of contextual information. You miss a lot of the information that actually brought the person to writing that text. On the other hand, every single document that Snap has an image associated to it. So the idea came, how can we leverage the image? And it is true, like that sometimes the image won't help and so on. So at the beginning, what we try to propose is let's combine them. Let's find a way to fuse the image and the text and the characters and so on. And also on one of the papers, for example, uses what we call modality attention. If there is any image that won't help, or any part of the input that won't help, like word, if it's out of vocabulary, it probably won't help and so on. There's any kind of image that won't help, let's use this modality attention that will lower the impact of the input, right? So our whole idea there was like, if we can, let's leverage images, but most of the times we might not even need to do that. So that was the idea. And then we worked on those papers. If you're interested, those are in the bottom. The problem is after those papers got some traction, a couple of citations and so on, people created more data sets. People keep, I started actually reviewing a lot of those papers for other journals and for some conferences as well. And what I started seeing is a recurrent overconfidence on how on a small data set like we had, like the one we created was this Twitter one, 2015, which has around 8,000 tweets. There was another one released in 2017 that has a little bit less than that. But people were overconfident on the kind of associations that text and image could be done with such a small amount of text and images, right? So example here of modern baseball, where modern baseball actually means a band, and highly unlikely that anything related to a band in this case could point out to modern baseball. Anyways, it's hard to tell exactly, but I started feeling, especially from the examples that people pick for the papers, that there was some kind of overconfidence on what's going on, right? So to give an example, and this is actually a pretty good paper. I'm not saying anything bad about this paper. I think even it's worth reading, and after we're done here too. But this is kind of the state of the art that was published in ACL of last year for entity recognition, multimodal entity recognition. What I take from this image though is there's a BERT encoder, there's a ResNet, two huge models already, right? Vision and text. You only have a small amount of image text pairs, which is a data set, mainly like 4K for training, 5K for training. But still, like there's a very complex fusion method there where you can merge the information from the text and the images, right? So I started wondering, how can we make this simpler instead of throwing more complexity on how you merge images and text, which are not there yet. There's a lot of work like Visual BERT and so on, VL BERT, that try to do that. On social media data lists, we're not there yet. Those were not as helpful. So the idea that we had is basically, what if we put the images in the same space as the text, but in a space that we already know how to combine? And the way we did it is basically getting an open source method, transforming all the images into image captions. And now we're representing the image by the image caption. Our input is the text concatenated to the caption. That's all we have as input. Then we're gonna feed that into a pre-trained language model, could be a BERT. We're gonna feed like some couple layers on top of that, and we're gonna make a prediction. So very simple on the fusion part, right? It's still complex, still have a huge model that does the captioning. There's still BERT that's been pre-trained before. It's big as well. But the fusion part here is done by BERT itself. It's not done by like a huge complex fusion method, right? And by analyzing the results that we got, we saw that, okay, it's not the state of the art, but also it is very simple and it's very easy to implement, honestly. It is state of the art on on the data sets. It is one of the most competitive ones. Actually, the second best, like now that I relook at the second best, only losing to the previous architecture that I showed, which you can see like it's also like the top of the line for most data sets. And but it's so simple, and you can see where things are going wrong on the fusion part, because as we're doing the error analysis there, we and this is not published yet, we have it on archive, but I thought it was worth mentioning here. As we see in the comparison, usually the problems come when the image captioning method fails. So no complex fusion techniques like BERT takes care of it, exactly because it's all text, right? There's no image text relationship. And at some point, it could be debatable, and I don't want to make that claim here, but it could be easier to do error analysis. So we looked at the image captioning, and most of the times the bugs come from when the image captioning is not great. So if we improve the image captioning, we could potentially also improve that part, but definitely more reliable, because we know that we don't have to make it super complex. We know that at least the relationship between the image and the text is not overfitting. because that is already known that BERT can do it. A lot of publications worked on that. And that's what we've seen after putting that into use, is that we can trust more this. There's no, like, they might make mistakes, like their accuracy is pretty similar on those two data sets benchmarks that we did. But in real life, when a more weird situation arises, the captioning system actually fails less than the, like, at least it's easier to understand why it's failing, because you can just look at the image caption. So the reliability kind of made us think about introducing image captions instead of just trying to make more and more complex systems for images. Again, not saying that making complex systems is a bad idea. I'm just saying that also making simple systems is a good idea as well. So let's try doing both and see which ones can get the best return for science and for usability. Okay. Another important thing as well is that if you do image captioning, which is very restricted explanation of the images, we don't have to keep the image, which is a little bit more like privacy constrained, which is good. Like now, if you don't have to keep the images, we can actually just have an explanation that's not identifiable, the persons that are there. We already only analyze public data, but we also delete public data every 24 hours. So that gives us a larger window to analyze that data. And we can keep the privacy bar very high, like we usually do for other tests. And privacy actually is one of the things that brings the most kind of projects to us. And let me talk a little bit about that, right? So privacy, we've been looking a lot, especially not on the NLP side, but also on the NLP side, on how can we leverage machine learning without no personal identifiable information, the most as possible, right? So as much as we can throw away your age, your gender, your any information that other companies use, we want to do it because we have no interest in doing that, and that kind of pushes us to doing more research in that area. One of them we published at Kai recently is the advertising. So basically, instead of actually looking at a lot of information for you, we only look at anonymous data of how, like, what times of the day or time of the day in the week that person, that anonymous user, interact with ads. And what we learn is that people interact differently during the day, during the week. On this work, also this other work that we published at ICWSM this year as well. But basically, the timing where you show ads, where you use your features and you notify users, all of those actually matter a lot for like cyclicity and so on. They actually matter a lot for targeting, without even having to think about like what other information we have from the users. So we've been investing a lot on that, only using in-app signals without having to know anything else from the user. There's a lot of great things coming up from Apple, like iOS 14, that's been great for the community of people that actually care about privacy. Google has passed some of those as well. So good job on that front. And we want to keep pushing that from our side. But one specific problem that was more on the NLP side was when I was, one of my first projects at Snap was to devise a language identification method that would not involve PII. And it will also work well in our data, right? So if you're not familiar with language identification, it's very simple. You have a piece of text like my name is Leo, or me llamo Leo, or meu nome é Leo. I put 3 languages that I can pick here, so make sure you're not writing anything offensive or anything like that. And the goal is, given the piece of text, you need to say which language it was written on. Okay, so very simple. Also, people don't even think that's an interesting problem anymore because mainly it's being kind of solved on other tests. But for our kind of data, it is still very challenging. Using any kind of open source method that we can find doesn't work well. Like, I'm going to show a graph, but drops performance a lot as we go with less words, which makes sense. You get less context. And there are some challenges inherent already very hard from language identification. For example, labeling social media data is complicated. and labeling any data, but especially social media data, is complicated because for you to label the languages, you kind of need to know which language it is. So you kind of need to at least have an idea of how to of the language, and no labeler knows like 40 languages, right? So what most people do is they use the metadata from users. Like, for example, let's say that you know that you're using your keyboard, and then you have multiple tweets, I don't know, using the same keyboard. So I could go there and see, that person mostly, like 2 or 3 of them, that person mostly writes in English. So we can safely label all of them using English, or you can use some other metadata like locale and so on. So all of those, we're trying to restrict as much as possible how much we had to know about the user, right? And I mentioned, like, the open source solutions are not great for short text. And we started thinking about how to be creative about labeling the data without having to know anything about the users. And that's what we came up with, right? We, instead of focusing on the model, which has already been super studied, there's a lot of great resources that kind of convey that, like naive Bayes, for example, is a great method. There's some deep learning methods there as well. But we kind of focus on the data collection step, right? So let's say Paris, for example. We got the first step of the data collection is just, we got a data set, just a random sample from the public stuff that we had, and we just labeled them into English or not, which is much easier to do, right? Like, if we know if the person speaks English, they can tell if something's not English. So English or not, English or not. And we also got a couple of open source methods, and we ran that on those as well to make sure that there's some agreement. And then basically, after we got a very good model that was able to detect if it's English or not with high precision, right? We could just put a bar of confidence level. What we did is we got all the public stories or public posts that happen on some like capitals of countries that we wanted to label the languages from. So in France, for example, we would look at Paris, and we would go on a holiday, which was very likely to be like a national holiday that local people would care about. So on the case of Paris, we got Bastille Day. And basically, by analyzing, like getting a couple of tweets or snaps in our case from different countries on that scenario, where we get just a very important holiday for that nation in the capital and so on, we saw that most of them are either French in this case, or the local language, or English. And using our language identifier now, we can just get that huge data set from that day, and we can predict if it's English or not. Everything that's not English, we can assume, a bit of noise, but that's fine. We can assume that all that data is French. And then that's how we label the data. We got like millions and millions of data points by doing that. And that's kind of the result we got here, right? So it's not focusing on the publication, but because we were able to add more data, and this is using a public benchmark, a couple of public benchmarks, and also our own like benchmark, we were able to get to results like this. A big improvement when you have less words, but also a big improvement when you have more words, like less than when you have short captions, but still, because of the amount of data that we could use, which is not as simple to do sometimes, we're able to get very good methods. Though the idea, through this idea, we got kind of more domain-specific, a better domain-specific model. We started writing a paper on this. It actually didn't get accepted at first, and we had the internal issue where we lost most of the experiment. So I ended up not publishing this work, right? But so if you want to try it again and do, it's open there. I don't mind. I hope that this is an interesting way for you to just approach the problem, right? So what we figured out is that it would beat the state of the art back then by large margins on short text, even out of domain. Even when we went to formal text, it would still beat the state of the art there on the other benchmarks. it didn't get it wasn't accepted at first, even though the reviews were good, mainly because there was a focus on the model that was not super novel. Again, I was not, the focus of the paper was not the model, but it kind of got stuck there. But the truth is, we were able to use this model and replace private APIs that we pay millions a year using this API, getting better results just by the simple idea that we had that doesn't even involve changing the model that we had in the background. So that saved millions and millions of dollars. It keeps saving us in this couple of years that we have been using it. And I think it's a very relevant point because it doesn't matter if it was not complex, but it was super useful. And I think it could be used by other people that care not only about metrics, but also care about privacy. And if they want to create one that's in the domain, right? So, okay, I've been talking a lot about the work we've been doing, simple methods and so on, but this is a workshop about peer review articles. And it might be, at some point, be looking a little bit different than that, right? I'm focusing a lot on simplicity instead of talking about peer review. So let me talk about peer reviews now. The reason why I been talking about all those works is because if you've seen, like, most of them have been published, some of them have hiccups and some will be published. We're just working on those. But for the ones that have been published, I got some reviews like this, right? So although the method is novel, is simpler, doesn't improve all the time the scores. Even though it's simpler, it spends many less resources and gets the kind of same results. The reviewer didn't think it was a good contribution, which is okay. Let's see some of the other ones. So smart way to gather data under privacy preserving settings. I'm talking about the language one, of course, but the model is too simple, not novel. I wonder if this model could be improved. This one I got several times on a lot of those, but basically I propose a simple solution and the person and the reviewer says, like, it could be improved if I added X, Y, and Z to this. Yes, it could. That's the idea is exactly not adding that and still getting good performance. And those all kind of, depending on the situation, and I'm not even saying that those reviewers are wrong right now, but depending on the situation, those could be like reasonable comments, at least, should be made. It's my opinion that those are not reasons to reject the paper, but that's okay. But I also got some comments like this. It's hard to find a reason to accept this paper. The same paper, we didn't change anything. We submitted to a new peer review system, another conference, and it got accepted the same way without many changes. Actually, we changed a little bit from the other reviewer that was a little bit more dedicated to the response. But this is one of the situations where, for me, it was very hard because I think, one, this doesn't really help the person that's writing it. You might be affecting a junior researcher. And I do feel it's like our role to improve this kind of system. So that's why I'm mentioning that we shouldn't discard research that's just simple, right? Let me actually quote Cynthia Rudin. She gave a keynote on Scalability 2019, amazing keynote. I recommend you watch it. I put it on the bottom here because it's very good. And one of the phrases that she mentions there is that complicated models are much easier to construct than simpler models. And that's not to say that complicated models are not important, that people shouldn't be working under like no constraints at first, because that actually helps. If you don't have constraints, you can actually put the constraints later. But if you start from a constraint, that's usually harder, right? Because if you can just throw more money, more layers, more resources, you might like eventually get better results, even by chance, right? But that's a different discussion. So this is a phrase that stuck to me, and I do think that if you like this talk, it's worth you going from the KDD 2019 keynote if you haven't watched it before. But my point here is, I think for us as reviewers, we have a lot of reasons to reject a paper. But some of those reasons shouldn't be that the idea is just simple, even if you saw the big impact that has, and it's something that's novel, right? The idea is novel, simple, but the scores don't really matter that much. The important is the idea and how applicable those are. I I think a lot of the more junior research specifically, but even a bit more senior researchers, they focus a lot on improving metrics that, like, there's a lot of other research that shows that a lot of the benchmarks are still we're almost overfitting to some of the benchmarks and so on. Also, like, if you see a simple idea, you're trying to combine that idea with a more complex one, and like blaming the person for not doing that, that's not a very good idea to reject the paper. I think you should, yes, be very strict on the way you review your papers. You should reject any paper that's not polished, it's incorrect, it's not a good fit for the conference. There's multiple reasons, right? Even if the simple idea is simple, but it's not effective, like, there's a lot of reasons to do so. But even when you have to reject the paper, remember to give proper feedback. First, think about yourself, right? Like, the other way around might be you that might get a bad review. But the truth is, your job as a reviewer is not to reject the paper. It is to protect the conference, protect research from work that's not there yet, but also to improve the scientific progress that you're contributing to. The review will help you help the society as a whole. If you get the other researcher that's still either junior or they didn't have time yet to polish the work, or there's multiple reasons for the paper to not to be ready to be published. But if you provide feedback, you can actually help that person grow faster. And then you're going to have more researchers focusing on improving society and improving research and so on. So it is a very important role for you to be a reviewer. Take that seriously, give your feedback, don't do things rushed, get less reviews if it's the case. I know we under this pressure of too many work pieces and not enough reviewers, but if you're gonna volunteer, don't do it just for the sake of it. Like, do put your effort there, give proper feedback, because that's how we're gonna advance the scientific progress. Okay, so keep that in mind. Be kind to people when you review, and please don't shut down simple ideas just because they're simple. Shut them down if they're not good, but if they're just simple, like, have an open mind to that. Okay, so I think I'm running out of time here, so thank you so much for watching. I cannot take live questions right now, but I'll be super happy to take any questions. Either you can add me on LinkedIn, reach out to me on my email, or contact the organizers. I'm happy to answer those written as well. So thank you so much for being here with us, and I hope you enjoy the rest of your workshop. Take care, everyone. Bye-bye.